All right, everybody. Today's video lesson is going to cover molecular geometry. Don't let that word geometry scare you. This isn't geometry like you have in your math class. This is really a fancy way of saying molecular shape. Okay, it's considered molecular geometry because if we look at the molecules, we're going to have the hydrogens. This is water here, by the way. Okay, so this is the molecule for water. When we look at water, we find that there's actually this angle between the hydrogen atoms, and that's why we call this a geometry, because when we're looking at the atoms here, we're looking at the fact that there's an angle between the atoms that are in here. So you can see there's a different angle in this structure here. This would be carbon dioxide, this is CO2, this is CH4. So our molecular geometry, the fact that we have arrangements of atoms at particular points in our structure, and they're going to have a certain angle away from each other, are what we're looking at. Now in chemistry, well in nature, we don't see the bonds. What we see are the atoms and positions. We know that these three elements, the two oxygens and the carbon, are perfectly in line with each other. But when water forms, it actually has a bent shape to it. It's not straight across. We actually have hydrogens above and the oxygen slightly below. Now it's three atoms just like carbon dioxide, but we get two different shapes or two different geometries. This over here is carbon, and carbon can take on two different forms, that of diamond and that of graphite. And why does that happen? Because again, it's the electron, or the arrangement of the electrons in carbon, and it allows it to form two different forms. Diamond, which is the hardest substance in nature, and graphite, which is a soft, slippery substance that you use in your pencils. Okay, so that is all from the arrangement, the three-dimensional arrangement of the atoms in a structure. So our Lewis structure, now keep this in mind, is going to show the arrangement of the valence electrons in a molecule. It's not really showing us the shape. So be careful with Lewis structures, and if you have trouble with Lewis structures, go back and watch the videos, go back and ask some questions when I see you in class about Lewis structures. I'm assuming you can do Lewis structures very well at this point. All right, so when we draw the Lewis structure for water, we have hydrogen, we have oxygen, and we have hydrogen, and we get two lone pairs or non-bonding pairs of electrons on oxygen. Now, I can draw the Lewis structure like that. That's a correct Lewis structure, but it does not tell me anything about the three-dimensional shape directly. I can get a false idea that this is linear. So be very careful when you are interpreting Lewis structures. They can mislead you if you're not careful. You could draw it this way, but you have to kind of remember to draw it this way, which is fine, but again, this is acceptable and this is an acceptable Lewis structure. I'm going to ask you what's the shape, what's the molecular geometry. Now to do that, you have to know something about what's called the valence shell electron pair theory. Okay, or in this case the valence shell electron pair repulsion theory. I think I would say repulsion. It's referred to as VSEPR, and it's basically the fact that electrons repel each other. Okay, that's what's going on here. So if I just look at my little molecule for water that I drew with the Lewis structure, well, because these are electrons and these are electrons, they're going to repel each other a little bit, and we're going to end up with this bond angle. Now, that is very deceiving because it looks like they're coming together. All right, so let's take a look at how we're going to clear that up. All right, so when we look at this, the idea is that we're looking at electrons repelling each other. All right, so I have this little animation I'm going to show you, and I'll actually have models in class that will help you understand this as well. So let's take a look at this animation that I have. Okay, what I have here is a structure, and don't worry too much about what the elements are. We're not concerned with that for right now. We're just looking at what they are. So, the fact that there are three elements, two different ones on the outside, one in the center. This is considered what's known as a linear shape. It's linear because it looks like it's in a straight line. So these two atoms are going to be 180 degrees away from each other. We refer to this as a linear molecule. Why is it linear? Because the electrons that are in my structure here, right, these are the bonds that are holding these two atoms together, bonds holding these two atoms together, are going to try to get as far apart as possible. And what they're going to do is these electrons are going to repel, and they're going to get 180 degrees away from each other, giving us our linear structure. Now, what should happen if I had a structure that was three atoms? Well, if I inject a third one in here, these are going to push away, and what I'm going to get is what's known as a trigonal planar structure. So notice that that linear shape is now pushed down, and this new set of electrons, based on the third element that's in here, are now going to repel each other. So if I have three areas of electrons around a central atom, I am always going to get what's called a trigonal planar structure. These are going to be 120 degrees away. Now take a look at this. This is going to be flat. It's a two-dimensional molecule. So from this angle, they look like they're 180 degrees away because it's a flat molecule. and we end up with 120 on this face, okay, in this face of the structure. That's referred to as a trigonal planar structure. We then have the third class that you're going to look at, which is a tetrahedral. This is when we have 4 atoms in here. If we go back to trigonal planar, we're just going to inject another bond in here. If I put another bond in here, these are going to repel, and it's going to reorientate itself so it now looks like this. Okay, so 3 dimensions. We got one of these bonds coming out, one of these atoms coming at us, another one going back into the screen here, and the other 2 kind of on the same phase. So you can see that this is a tetrahedral structure. Again, it has a 3-dimensional look, and that's what you got to keep in mind. All right, so if we go back to our model here, our theory, these are the 3 that we looked at: linear structures, trigonal planars, and tetrahedrals. So if I have 2 areas of electrons where these electrons are negatively charged, okay, it's a negative charge here and a negative charge here, because those are electrons, they're going to repel each other and try to get as far apart as possible, and therefore those atoms are 180 degrees away from each other. You inject a third one in here, you now push these 2 down, and you end up with 120. Trigonal because it looks like a triangle, and planar because, as I showed you in that animation, it's a flat molecule. All right, and then you have your tetrahedral structure, and the tetrahedral has that 3-dimensional look where it looks kind of like like a pyramid in a sense. Okay, so you picture this as a pyramidal shape. This would have a face here, and this would have a face here. Okay, all right. So one thing to keep in mind about this is the tetrahedral one throws students off all the time because they see 4 areas around a central atom, and your first instinct when you see 4 atoms around a central atom is to think that that's going to be 100 or 90 degrees away from each other, because you're thinking of it as a flat molecule. So be careful with Lewis structures. Lewis structures will mislead you if you're not careful. I'm going to show you in the next couple slides how to make sure that that doesn't happen. All right, first thing we need to look at is the fact that we have 2 different types of bonds, 2 different types of electrons. All right, we're going to look at electron areas, and what that means is that's the area around the central atom. So let me show you 2 examples. I'm going to throw that methane back up here. This would be CH4, and that would have 4 hydrogens around here, and again, I'm assuming you can do that. And let's look at ammonia. When you do the Lewis structure for ammonia, you end up with 2 lone pairs, or one lone pair of electrons here, okay, or 1 non-bonding pair, and 3 bonding pairs. So what we do is we look at the center atom, okay, and we look at carbon and we look at nitrogen. There are going to be bonding and non-bonding pairs of electrons, and both of those count as 1 area of electrons. Don't let that throw you off. Here's what I'm saying. 1 area of electrons, 2, 3, 4 areas of electrons around that carbon. 1, 2, 3, 4 areas of electrons around that central nitrogen. But they're going to be different, and the difference lies in the fact that I have that lone pair of electrons here. Okay, one other thing to look at is that if I have something with a double bond in there, like carbon can double bond with oxygen and can make a hydrogen here, put a hydrogen here. If I'm counting these areas, I'm going to count double, single, and triple bonds all as the same. So what I would do is 1, 2, 3. Even though there's 2 bonds here, it's still the same shape as if it were a single bond. So 1, 2, 3 areas. So on this structure here, I have 3 areas of electrons. So 3 on this one. 1, 2, 3. Okay? All right, so what do I do after I figure out how many areas of electrons I have around my central atom? Okay, but counting bonding and non-bonding as the same. Now what I'm going to do is I'm going to separate out those bonding and non-bonding. Let me show you that in the animation again. Okay, so this is methane. This is that CH4 that I had drawn the Lewis structure for in the previous, on that previous slide that I showed you. Notice what happens here. This forms a tetrahedral structure. All 4 of those areas are bonding because we're looking at where are the atoms. The atoms are here, here, and here. So those are where the atoms are located. All right. So if I look at ammonia, NH3, here's my hydrogens, but notice that I have those lone pairs of electrons up here, or non-bonding pairs of electrons. Those are electrons, and they're pushing those atoms down because there's electrons here. So I have 4 areas of electrons. So if you look and compare, it looks kind of like the tetrahedral shape. Right? They look very similar, but I have an empty space here. There's electrons, but they're too small to see. So all I'm doing is taking off that top portion. All right, and then I can go to my last structure, which would be a bent structure, where water. If you draw the Lewis structure for water, you might remember that water has 2 lone pairs of electrons, or two non-bonding pairs of electrons above. And this pushes those bonds down a little bit, again repelling those electrons, giving me a bent shape to the water molecule. Okay, so that's going to give us all the shapes that you guys are going to be required to know in this class. So you have your linear structure, your trigonoplanar, and your tetrahedral. Okay, I already gave you this handout. So what we do is we count the areas of electrons around there, and we say, okay, if there's two areas, are they all bonding or are there any non-bonding? Well, for linear, all you can really get is a linear structure. So it would be, your molecular geometry would just be linear here. Trigonoplanar, that would be three areas of electrons. So if I were to do boron trichloride, well, if I draw that Lewis structure for boron trichloride, remember, boron should be a deficient octet. I'm not going to draw all these electrons. You guys can kind of assume they're there for right now because I'm focusing on the center atom. Three areas of electrons, 1, 2, 3. All three are bonding. There are no non-bonding. I would say that that's trigonoplanar. Okay, if I did tin with the chlorine, I'd have two chlorines on here. Again, you can draw the electrons around here for yourself, but more importantly, there's going to be a lone pair on this. So I have 1, 2, 3 areas around the central tin. Two of them are bonding, one is non-bonding. So this one isn't there. You can't really see this one in the space, so you see this bent shape to the structure, so therefore bent. Tetrahedral, 4 areas are around it. All are bonding. We consider it still tetrahedral. 3 areas, one of them being non-bonding, would be considered trigonal pyramidal. And if you take 2 off, and you end up with just this bent structure. So 2 of them are non-bonding. Okay. So let's go through the rules. I know you're probably really confused, and students typically are when the first time I go through this. So we'll get all the questions answered in class. So let's just finish this up today real quick. Here's your rules for writing Lewis structure. For writing molecular geometries. Step 1, be able to write the Lewis structure. Go back and be able to do that. Then 2, we're going to determine the base structure. Count the number of areas of electrons around the central atom, including bonding and non-bonding pairs. 3, determine the molecular shape. To determine the molecular shape, you're then going to determine how many are bonding and how many are non-bonding. So, for example, let's say that I have SeS2. Okay. Well, the Lewis structure for that is going to be Se with a lone pair of electrons, a double bond on the sulfur, and a single bond. I put my electrons here, here, and here. So that's step 1. Okay. Now, I don't have to worry about drawing that in any particular shape because I'm going to determine the shape based on these step 2 and step 3. So what is my base structure? Well, I count the number of areas of electrons around the central atom. 1, 2, 3. Remember, I count double bonding and single bonding is the same, and I count lone pairs of electrons. That goes back to this slide right here if you want. Okay? That's the rules I'm using to figure that out. Alright, so that's step 2. Step 3. Then I figure out 1, 2, 3. So then I go to my chart. 3 areas of electrons. I have a base trigonal planar structure. Okay, that's my base structure. Then what I'm going to do is I'm going to say, okay, how many of these are bonding and how many are non-bonding? Well, I have 2 bonding and 1 non-bonding. So I look on my chart. 2 are bonding, 1 is non-bonding, and boom, my shape is bent. So I would say that this is a bent shape. Okay? And that's how you determine the molecular geometries. You don't have to draw it. You don't have to actually sketch it out. You just have to say bent. Alright? We'll definitely look at this more in class. I know it's very confusing in the beginning, but I will definitely get you through this in the next couple days. Alright, thanks a lot, guys.